All right. Good morning, everybody. I'm doing this because I haven't found a good video or any other kind of good explanation about how to do floating point or fixed point, actually, math in hardware, in an FPGA. There's all sorts of pontifications and so forth that are really good reading material that explain the math of it and so on and so forth. But took a lot of time to go through and understand. So, and me being new to FPGAs, I'm trying to write my own fixed point library. So let's start off with regular division, base 10. So, I don't know, let's choose a number, 53 divided by 3. Nice easy number, we can do this, right? We've done this so long that we don't realize what we're doing. We've forgotten the actual steps, they've become automatic. It's hard to describe. So, 53, this is the 10 squared, 10 to the 1 power, this is 10 to the 0 power. This is 10 to the negative 1, 10 to the negative 2, and so on, 10 squared, and so on. So what we're doing is, the first thing we're doing is we're actually we're aligning this 53 divided by 30. We're doing our operation here. So when we go here and we say, oh, well 3 goes into 5 one time, multiply 3 by 1, 3, we subtract the 2. What we've really done is we've said 30 goes into 53 one time, 30, and we subtract and get 23. Well, now I know that 3 goes into 23 7 times. 7 times 3 is 21. I subtract, there's a 2. And we can go on and we can say, oh, remainder 2, which is equal to 17 2/3. Or we can keep doing the math, right? I can put a decimal point here and a decimal point there, put a 0, and say if I carry this 0 down, because there's an infinite number of zeros this way, in fact there's an infinite number of zeros this way, so it doesn't matter, they're just implied, right? So now we know that it's 6 times 3 is 18, and I get a 2, and I can look at that and say, oh, well, I'm going to get 20 again, and 20 again, and 20 again. So it's 17.666 ad nauseum. Easy. We all know how to do this. We've forgotten the steps, what the steps mean, I think, a lot of us. And so that's why I did this, just to help us remember that. So let's talk about 2 binary numbers. Again, to pull a number out of my rear end, let's go 0, 1, 1, 0, 1. 1. So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and we know that this number then is, this is 1, 2, 4, 8, 16, 32. So I know that this number 16 plus 8 is 24, 25, 26, 27. So this is 27. And let's choose another number. 0, 1, 1, 1, 0, 1. Nah. Let's make this easy this time around. 0, 0. So we know, again, 4 plus 1 is 5. So 27 divided by 5, we know how to do that. How do we do it in binary? Well, binary, we do the same thing. We set up our long division. And this is stuff that you can find anywhere on the internet fairly easily right now. So here we put our dividend, 0, 1, 1, 0, 1. And then we put our divisor, 0, 0, 0, 1, 0, 1. Now, again, these are implied, so we can just erase these. And what we need to do now is we need to left align, if you look at this as though it's a register that's got 0, 1, 1, 0, 1, 1 in it. What we need to do is we need to take our divisor and we need to left align the very first 1 in a matching register, 1, 0, 1. Now we're going to do what's called shift and subtract, or you'll see that this is the same as shifting and subtracting. So I say I've got 1, 0, 1 here. I'll do it in a different color so that we know. So I've got a 1, 0, 1. Well, I know that 1, 0, 1 is bigger than 0, 1, 1. So I also have to know this. So my answer is 0, and so I subtract nothing, and now my answer is still 1, 1. But now I right shift this 1, which is what we were doing in the decimal system, right? And so now I want to say, well, 1 times 101 is 101. Drop this 0 down. And 101 is smaller than that. So, in fact, I subtract and I get that now. So we keep doing this. Well, now I left shift this. I'm losing my alignment. This is the problem of doing this up on the whiteboard. That's a 0, that's a 1. Well, now I say 1, 0, 1 here, but that doesn't work because, let's see, I dropped that 1 down. Because 1, 0, 1 is bigger than 1, 1, 1. So I put a 0 there. And now I move 1, 0, 1 over here. And now I subtract and get a 1, 0. So that's a 1. And now I'm done. So, again, 1, 2, 4, this is 5. 5 times 5 is 25. So, and then there's a remainder of 1, 0, which is 2. So 5 times 5 is 25, plus 2 is 27. So our math works. Awesome. So what do we got to do here to do this in hardware? The first thing is we need a series of, when I first get my number in, I've got divisor, and I've got dividend, and I've got quotient. So I'm dividing. I need to have a register that's as big as each one of these so I can make a copy and not lose things. And I can say, oh, well, dividend is equal to dividend. So it's what it was when it came in. Divisor, I have to do a loop. So it's something approximately always at pause edge clock. We will do an if dividend, and we're going to say it's n bits long, so it's n minus 1 down to 0, right? N bits. So if dividend underscore copy, we'll call it copy, that makes more sense, that's easier to div under copy, d under copy, of n minus 1 equals 0, then d under copy is equal to d under copy left shifted 1. And we keep doing that until if this is not true, if D underscore copy is done, then we end. So put a begin in here. And now this could be the danger here, of course, is if there's a 0 in your dividend copy, this will run forever and never get anywhere. So you need to detect that somehow. If this is a 1, if there's a 1 in the leading bit, then it takes no clock ticks at all, or it takes 1, it zips through and it's done. If it is only a number 1, well then, or if it's in the least significant bit, then you have to do n bit shifts, or I guess n minus 1 bit shifts to get there. So this is non-deterministic in time. Now, that's great, this is tight, this is compact, it's not bad with hardware, but let's look at the way I've been doing it is deterministic in time, and that is it'll always take exactly the same amount of time to finish no matter what. So let's take a look at that, and it's the same thing. We'll use the same numbers, and the first thing we'll do is we'll create a register, and this register will have, I'm going to do this, I'm going to write this slightly different. I'm going to put my quotient over here, and I'm going to put my dividend here, which we know is 27. 1, 1, 0, 1, 1, 0. And I'm going to put my divisor over here. And I'm going to do something a little different. How many bits is this? 1, 2, 3, 4, 5, 6. It's a 6-bit number. So I'm going to put in 6 zeros, 2, 3, 4, 5, 6. And now I'm going to put my divisor. 1, 0, 1, 0, 0, 0. So this buffer is 2 n minus 1 bits wide, right? Or actually it's 2n bits wide. This is position 2n minus 1. And this is position n minus 1. So what do we do here? Well, this, on the very first thing I did was, when I handed this over, the very first clock tick where we latch everything in, I latched it over here. So I'm using more bits. Oh, and I need a count. I need a count. And you can't see that because it's off the screen. So, but you can see it here. So I'll put a count here. Count. So the first thing I'm going to do is I'm going to set my count to n minus 1, or to n minus 1. N minus 1. So in this case, n minus 1 is equal to 5. Sorry, set my count to n equals 6. No, that's right, n minus 1 equals 5. Got it. So the very first thing I'm going to do is I'm going to take a look, and I'm going to say, is this number smaller than this number? So this is all zeros. 3, 4, 5, 6. So is a lot of zeros 101 smaller than this? The answer is no. So I do nothing. I right shift 1, 0, 0, 0, 0, 1, 0, 1. Make sure I'm not losing my columns. Nothing changes. Is this number, 5 zeros, 101, smaller than this number? No, it's not. So, oh, and I decrement my count. So, count is now equal to 4. Now, I'm going to right shift again, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0. 3. My count is now 3. This hasn't changed. Is this number smaller than that number? Again, the answer is no. It won't be for a couple more shifts, so let's right shift one more. So I decrement 2, I decrement 1, my count, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0. Is this number smaller than that number? Well, by golly, no, it's not. So let's decrement our count one more time. 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 1, 0, 1, 0, 0. Is this number smaller than that number? Well, yes, it is. So if this number is smaller, well, now I need to subtract, just like we did in decimal. So now, if I subtract 101 from this, this becomes 1, 1. Carry this 1 over to here, he becomes 0, 0, 0, 0. Right? I think I did that right. So now that's my number. And what happened was I said, nothing changes, nothing changes. But here something changed, and it was there. And I counted, and I started my count wrong. Dagnabbit, I hate it when that happens. It should have been 6. So it's N. Because that one will never happen. 6, counts 5, counts 4, counts 3, counts 2. My count should be set to N, I apologize. And so now, over here, quotient of count becomes quotient of count 0, 1, 2 becomes a 1, and my new answer is now this. I did the subtract. So now I decrement one more, and I 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0. Is that smaller than that? Well, no, it's not. So I've lost a bit here somewhere. Something weird going on. I might have to re-record this video, we'll see. So that didn't happen. So now did I do my subtraction wrong? Oh. I did do my subtraction wrong. That should be a 1, shouldn't it? If I add a 1 to that, it carries over to there. Yeah, that should be a 1. That's what's wrong. I did my subtraction wrong. All right, so now I've right shifted to there, and so no, this is not correct. 0, 0, 0, 0, 1, 2. That becomes a 1. It stays a 0, but now I right shift one more time. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1 is less than that. And if I subtract 1, 0, 1, I get 0, 1, 0. But bit 0 just got set. Lo and behold, my answer is 5, which is the same number we got before. And I know I'm done because my count's 0. So I set my count equal to n. I right shift 1 bit every time. If the dividend is greater than the divisor, then I set the quotient bit, so quotient of count, to 1, and I subtract. So we're doing the same thing, we're just doing it a little bit differently. And now I know that this takes exactly n counts to do every time. Every division takes exactly n counts. So determinism in time is sometimes a good thing. It makes your time enclosure easier, makes your timelines easier to figure out. There's a lot of good things about that. But I've paid for it because, well, in this case I've paid for it, but in perhaps a longer time to do the ticks through than if I did the right align at the beginning. So, in fact, now that I think about it, maybe this is equivalently fast every time. But let's take a look at this. Let's talk about fixed point for a minute. Let's look at a fixed point where we have a, can we see the top of the screen up here? Oh, you can't see anything I wrote up here. This is 2 n bits wide. And this number was 27, but now it's 5, so we know 5 times whatever our divisor was, 5 is 27. Remainder 2 again. All right. So let's take naively, let's look at this and say, well, I did my division, but this was fixed point, and we'll use the Q format that is a register that's n bits long, and q bits are fractional. So something like that. So, and the way this works is, I'm going to keep that number right there so I can see it later. I know my quotient. Okay. Whoops, I erased my dividend. It was 0, 1, 1, 0, 1, 1, I think, right? So in Q format, we're setting up a decimal, well, a binimal point, I guess. And here, just like in decimal, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, which is 1/2, 1/4, 1/8, and so on. And then over here, this side, 2 to the 0, 2 to the 1, 2 to the 2, 1, 2, 4, and so on. So I know before my division worked. Oh, and if you're doing integer division, let me talk about this for a second. Your quotient will never be bigger than your dividend. So you know right off the bat that the two are the same size. And the reason is, if you're doing integer division, the only thing you can do is divide by 0. So you have to check for divide by 0, because if you get one of those, well then that's infinity, not or whatever, right? And if you have a 1, which is your worst case, the biggest number you're going to get the same answer back out. So one of the nice things about integer division. So let's use our number here again, and let's just say, well, what if this was 1, 1, 0, 1, 1, 0. So let me give myself a couple more decimal points here. 2 to the 3 is 8, 2 to the 4 is 16. So, and if I divided by dividend, divisor, if I divided then by 1, 0.1, because in fixed point we assume everything's the same format, so this 1, 0, 1 also becomes a 1, 0.1. Well, so this is 8, 12, 13 and a half equals 13 and a half. and this is 2.5. I'm going to get out my calculator because I'm not good at math, believe it or not. There we go. 13.5 divided by 2.5. We know the answer should be 5.4. All right. But the answer we got was 101. So, but the answer, quotient was 10.1. And there would have been some more bits behind it. So, but this is equal to 2.5. Well, that ain't right, right? Obviously, we know it should be 5.4, and here we got 2.5, and that is not equal. So what's going on here? Well, let's try this again. What happens if I move my bits one more to the right? So what if this becomes a 0? 1 1 0 1 1 0. And so to keep my format the same, this becomes a 1 0 1. So this is 6 3/4, 6.75, and this is 1 1/4, 1.25. If I divide those two, I should get, oh, about 4. 6 1/4 divided by, no, clear. 6.75 divided by 1 1/4, 5.34, 0.378 ad nauseum. Well, but wait a minute. My answer then is 1.01, which we already know is 1.25 because I chose a case that turns out easy and my answer and my divisor are the same every time. Well, that ain't equal either. What's going on here? How do we make this work? This obviously worked for the integer case. Well, notice that if this case, I move it 2 bits to the left, well then it becomes 5. I've got my, I've truncated my decimal bits, my fractional bits, but that's pretty close. In the previous answer, if I moved it 1 to the left, well that was 2, and the answer was supposed to be 2 point something. So that gives us a hint right there, and there's big proofs about this all over the place. But the answer is that when you're using a fractional number like this, whenever you get the answer at the end, you have to left shift q bits. I'm going to sneeze. Excuse me. So now we know right off the bat that if I'm doing an n minus a q format number and I want to do a division with another q format number, when I get to the end I need to left shift q bits. But what you see here is that I'm truncating every time. Not rounding, I'm truncating. It might be the same as a round. In this case, it would be a round down, but in the case of the 10.1, which is equal to 2.5, I would truncate that when I should have rounded up to 3. So this is always going to give us an error in a specific direction, which is towards a smaller magnitude. Oh, and the other thing with division, in my fixed point format, if I put a sign bit in here, n minus q minus 1 now, then I don't have to do anything with the signs. I ignore them all the way through, and the sign bit in my quotient is the exclusive OR of dividend, the dividend sign exclusive OR with the divisor sign, which would be divisor of n minus 1, and this would be dividend of n minus 1. So, nice to keep in your pocket. You don't have to just ignore the signs. You don't have to do 2's complement or anything like that. Just at the end of the division, exclusive or the signs. And that's because of the math property of multiplication and division of negative and positive numbers, right? A negative times a negative is a positive times a positive is a positive, and a positive times a negative is a negative, and division is the same rules. So all you got to do is keep track of the originals and do an exclusive or at the end to get that. All right. So let's extend this whole mess then to a fixed point notation. And now it becomes some tricks. So we're going to need to do some alignments. Sorry for this pause. I'm opening up a spreadsheet where I've already done some of this stuff, so I don't have to worry about so much about making big mistakes. There we go. So let's do a real simple 8.1 type thing. So I'm going to have n equal 8, q equal 4, and 1 sign bit. So my registers then look like this: sign bit, decimal point, q is 4 bits, and this is n minus q minus 1, which is 3 bits. So 1, 2, 3, decimal 1, 2, 3, 4, and a sign. Okay? Now I'm going to divide, we'll call it 1.2, but the reality is whenever I push it in, 1.2 into this is going to be 1.0. 0.011, which is 1.1875. I'm cheating. I've got this up on my computer screen over there. So we've already lost some fidelity because we can't represent 1.2 in binary because it's an infinitely long string. And our divisor, let's make our divisor simple. Let's make our divisor a quarter. So that would be that, right? 1/4. So this is 0, 0, 0. I'm sorry. This is 0, 0, 1. 0, 0, 1, 1 is our dividend. And our divisor is 0, 0, 0, 0, 1, 0, 0, which is equal to 1.1875, and the answer, divisor is 0.25, and we know up front, a priori is the fancy name for that in advance, that this will basically be 4 times that. 1.1875 divided by 0.25 is 4.75. And that would be 1100010. So that's what our answer should be. All right, so we know this, right? Because we're smart and we're thinking ahead for a change. Now when we do our division, before I put my I put my divisor into a register that was 2n wide, or almost to end. Now I have a sign bit, so I'm going to ignore the sign bit. So it's going to be 2 n minus 1 wide, but I need to add q bits on the end, plus q. So I'm going to make that right now. So I know that my divisor, I don't have a big enough board for all this. If this is a school, I'd have like 47 of these boards and I could just keep writing all over the place. So n minus 1 is 8. No, n is 8, n minus 1 is 7. So I've got 1, 2, 3, 4, 5, 6, 7. And then I've got 1, 2, 3, 4, 5, 6, 7. And then my 4 q bits. 1, 2, 3, 4. So this is 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Q, that's an 8. Q, n minus 1, n minus 1. And my dividend, so this is my divisor, goes into here. And I push the divisor over to here, into the far left, and into the leftmost n minus 1 bits. So this is 0, 0, 0, 0, 1, 0, 0, and then all the rest of these are zeros. And I'm gonna have to erase these. 1.1875.25 divisor, dividend, divisor, and 0, 0, 1, 0, 0, 1, 1 equals 0, 0, 0, 0, 1, 0, 0, quotient is 4.75 equals 0, 1, 0, 0, 1, 1, 0, 0. All right, erase all this and get it out of the way. I'm going to move this all over. Sorry, wasting your time. So we'll have 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4. Dividend goes up here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Q bits, n minus 1 bits, n minus 1 bits. I said dividend? I meant divisor. Sorry, I'm going to confuse you. Divisor. And over here we put our dividend into n minus 1, 1, 2, 3, 4, 5, 6, 7, n minus 1, plus q bits, 1, 2, 3, 4. And we move my chair out of the way. And we set our dividend over here into the leftmost bits here. So 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0. And like I said before, our divisor goes all the way over here on the far left. So 0, 0, 0, 0, 1, 0, 0. And then this is all zeros. And then my quotient over here needs to be a space that's as big as the divisor, actually. But I don't have room on my board for all that, so I'll just write quotient over here for now. And it is also 2 times n minus 1 plus q bits wide. Now, we start off the same way we did before with integer division. We set all of our registers to 0, we move the divisor in, we move the dividend in. The sign bit of the quotient will be the exclusive OR of the 2 sign bits of the 2. And then we set our count to n plus q minus 1 is where we start our count now. Minus 1 because there's a sign bit in there that we're throwing away. Remember, we've got a sign, n minus q minus 1 bits and q bits. So this is 1 bit, this is 4 bits, and this is 3 bits in our representation. I don't know if you can see that up there. And now I do the same thing I did before. I just start shifting right, and if it's do the divisions. So my count here is n minus 1, n minus 1 is 3 plus 4, my count is 7. Does that make sense? Did I get my count wrong? I'm looking at this and right off the bat it seems wrong. 1, 2, if he was here, 1, 2, 3, 4, 5, 6, 7, but that, yeah, okay, that makes sense. No, that's where I'm making the mistake. N is 7. N equals 7. Q equals 3. 4. Or actually, N equals 8. So this is 8 and 4 is 12, minus 1 is 11. My count should be 11. Thank you. That's what was wrong. I'm old, I'm sorry. I don't always remember things the right way. So count, I right shift 1 and count goes to 12. So I know 1. And quotient of, let me see if I can get this in here. Quotient will be 11 bits long, or actually 12 bits long at the most. So 1, let's see, that'll be 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Which you can't see off on the right-hand side of the board there, I don't think. Let's see if I can zoom the... Oop, that's the wrong way. There, maybe you can see that now. Mine has just got too small to read though. Okay, so count becomes 10, decrement my count, I right shift 1. Is this big number here smaller than that? No, we know we got to get over into here first, so this is still 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, and this is all zeros. And now it's still all zeros. The 10th bit stays the same. So now I decrement my count and I right shift everything 1. Is this smaller than that? No. 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0. This is still a gob of zeros. 3, 4, 5, 7, 6, 5, 4, 3, 2, 1, 0. So I decrement my count and I right shift again. I'm getting closer. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And start singing a little song about ones and zeros and how they make our life, I don't know, not quite NP complete, I guess. 5, 6, 7, 8, 9, 10, 11, 12. And the zen of binary, I divide by 2 again, which is really what these are, right? Right shift 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. Oh, wait a minute. No, no, no. We're still not smaller. 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0. 6. Right shift 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. Hey, you know what? The divisor is smaller than the dividend at this time. It actually aligns with this bit. Oh, I forgot to do this. Hang on. 1, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So, hey, it's smaller. So, right off the bat, I know that Q of 6 is going to be 1. So, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And I'm going to subtract, so this becomes 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0. Awesome. Now I decrement, I shift 1, 0, 0, 0, 0, 0, 0, 0. This is monotonous, isn't it? This becomes the same. I know that that's this bit. 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Decrement again. I'm losing track of where I am here. 4, 1, 7, and 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. That's that one, so this doesn't change. 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, in my sing-song little voice. Decrement 1. 1, 0, 0, 0, 0, 0. Hey! 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This number is smaller than that number. So, quotient of 3 now. 11, 10, 9, 8, 7, 6, 5, 4, 3 becomes a 1. And when I subtract, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. Right shift decrement 1, right shift 1, 1, 0, 0, 0, 0. Well, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's less than or equal. So we know the quotient of 2 then. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. When I subtract, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Now, of course, there's 2 more shifts that are going to happen, but we already know that this and this are bigger than that. And had this been a 1 here, he would have shifted all the way across to there, and that would have been our last one. And had it been a 1 here, he would have shifted over here, and that would have been our last one. So anyway, what have I got here? My quotient, remember, should have been 0, 1, 0, 0, 1, 1, 0, 0. Go in the opposite directions. 1, 2 zeros, 2 1s, 2 zeros, and a 1. Look at that. Amazing. So my quotient then, the last 4 bits are my fractional bits. And I've just done a fixed point divide and come up with the right number. this is a way, not the way, this is a way to do a fixed point binary division. And it takes however many n bits you are. We have, there's a virtual sign bit out here, so we'll need a sign bit, right? And it'll actually be, this bit would become the sign bit. One thing you need to do is you need to check for overflows. If I had, say, for instance, my dividend was all ones, and my divisor was 0, just way over here, just this 1. Obviously, when we do the math, we know that we're going to get a lot of ones that are up here at the very beginning, right? And so that means we've got ones outside of our n-1 bits, so we have to check over here. If any of these are 1, or if this section is greater than 1, then we've got an overflow. So that's an important thing to detect. We know that we need some bits for registers. So we need 1, 2, 3, 4, 5. We need 5 n-1 plus 1, 2, 3, 3q bits in our registers. We know that it's going to take n plus q minus 1 shifts and subtracts, so that many clock cycles, excuse me, plus 1 more clock cycle to get it in, and maybe 1 to get it out. So this is on the order of n plus q clocks. Is there anything else I need to know about this? There it is. I'm putting this up on my YouTube page. If this is worth anything to you, thank you. I hope it is. I hope the explanation was halfway decent. Do this yourself. Use Microsoft Excel or something like that. Some good spreadsheet where you can drop numbers in and shift them one at a time and see what happens. Try it for all sorts of different numbers, or go search for some proofs. There are proofs out there, and if you're into that kind of thing, I'm just an engineer. I don't want to so much go through all the proofs, just understand how it works and implement it. So there you go. Bye all.